look at properties of rational functions. More specifically, we're going to look at vertical asymptotes and removable discontinuity. Vertical asymptote describes the behavior of the graph when x is close to some specific number. The graph of a function will never intersect a vertical asymptote because vertical asymptotes and domains go together. So something's excluded from the domain, then that's the place where we're not going to be able to cross or touch. More specifically, it's what's undefined in the domain, and there's one catch to that. Like, we can find the domain, but then once we find the domain, we write our asymptotes as x equals some number. And if you look at the box beside our left-hand box here, this picture didn't show up that well on our notes. You can see it a little bit better here, but the blue parts of the graph are the function, and then that pinkish color in between is the asymptote. We're getting closer to that dotted line, but we never quite touch it. Same thing in the second picture farthest to the right. The blue parts are the function, and we're getting closer and closer to x equals c. We don't know in particular what value that is, but that is our asymptote. It's a vertical line that the graph approaches and never quite touches. They never intersect it. So if we look at this example here, it says state the domain of the following rational functions, determine the vertical asymptotes, determine the x-intercepts, use your calculator to confirm your answer, draw a rough sketch of the function, be sure to draw in the vertical asymptotes. Well, we can even start with our calculator here. We can type in this function. If we go to y equals, and then alpha y equals to get our fraction button, and x plus 5, divided by x minus 2. And we look at the picture. There's our rough picture there. And remember yesterday we were looking at the domain of the function, and we said if there's a gap in this picture, then something is probably excluded from our domain. So as I put this picture in here, what it looks like is that we have a gap over here at 2. And just a reminder here that the denominator is where we can recognize that fact. We take x minus 2, we add 2 to both sides, and we get x doesn't equal 2. There's our domain. Well, as we draw our rough sketch, like I said, the gap seems to be at 2. That's where our vertical asymptote is. And domain and vertical asymptotes go together. Here's our domain, x doesn't equal 2. Our vertical asymptote is x equals 2. We draw the sketch here. And it's rough. But we need one more piece of information. And what that is we need to find the x-intercept. If we go back to our calculator and go to our table function by second in table, and we scroll through our screen a little bit, I actually didn't have to scroll very much. An x-intercept always has a y value of 0, and there is our x-intercept, negative 5, 0. If we look a little bit closer here, I wonder if we could figure out from the equation, how do we figure out the x-intercept? What we see up there in the numerator is we have this value of x plus 5. And if we set that equal to 0 and solve that equation, we end up with x equals negative 5 And again, I'm a little bit off on my picture there, but we do have an x-intercept at negative 5, 0. So let's look at another example here, and we want to find the domain, we want to find the vertical asymptote, we want to find the x-intercepts. And what could be helpful, possibly, is that we could use our graphing calculator to help us get a picture. So we'll go over here to the calculator, go to y equals, and we will type in our function, which is x divided by x squared. Oh dear. X squared minus 9. I'm going to look at the picture. And the nice thing with the calculators is we know that we're looking for the gaps, and we can see that there's a couple of gaps in our picture. And along with the equation, that can also be helpful in terms of domain. But as we draw a rough picture, what it looks like here is that we have a gap at 3, and we have a gap at negative 3. And one of the ways that we can do that, if we're not sure on our calculator, is we can look at the denominator of the function, which is x squared minus 9, and we can set it not equal to 0. And in order to solve that, we get x squared doesn't equal 9. And the inverse operation of squaring something is square rooting. And we end up with x doesn't equal plus or minus 3. Remember that 3 times 3 is 9. Negative 3 times negative 3 is also 9. So our domain, whether we see it in the picture, whether we do it algebraically, and we're going to look one more place, is x doesn't equal 3, and x doesn't equal negative 3. And if you would like to write x doesn't equal plus or minus 3, I'm fine with that notation as well. The other thing that you could look at on your calculator is we could go to second and graph, and there we can see the 3 on here has an error, and we have to work with real numbers. And as we scroll through our calculator, there's negative 3 with the error. So there's a lot of ways to identify the domain of the function. But the nice thing here, as I draw just a real rough graph of this, the nice thing about domain is that the domain and the vertical asymptotes have some things in common. And in this particular problem, we see that we have 2 vertical asymptotes, and the equations of those are x equals 3 and x equals negative 3. And if you look back at the box there, remember the vertical asymptote describes the behavior of the graph when it is close to some specific number. And it goes along with our domain. Finally, we can see by our picture what the x-intercept is in this problem. You probably see that it crosses right here at the origin, which is 0, 0. But is there a way that we can look at this from our equation and determine what the x-intercept is? Well, the denominator tells us the domain. The numerator, which in this case, the top of the fraction, can be set equal to 0 to tell us our x-intercept. try another one. Again, you may find it helpful to type the function into your calculator. Vertical asymptote. Vertical asymptote. Asymptote, yep. I'm told I say it a little bit wrong.
I think that would be silent.
Asymptote. Yeah, I think he's right. Look back at your definition. It describes the behavior of the graph when x is close to some specific number. It's a line that the graph approaches but never quite touches. And that's what our dotted lines are in example 1, in example 2. And then we'll see what we get on example 3. So we're going to go and we're going to type in this function, if we can. So we go back to the y equals, and we clear. Alpha y equals to get our function in there. And we type in x squared divided by x squared plus 4. X squared divided by, come on, x squared plus 4. And we look at the picture. And the difference between this problem and the last problem is that we can graph this function without lifting our pencil. There's a picture. And what we learned yesterday is if we can graph our function without lifting our pencil, then our domain is all real numbers. And if our domain is all real numbers, and we don't have a gap in here, that means that we do not have any vertical asymptotes. DNE does not exist is good. And then finally what we have to do on this one, and my picture is not very good. Let's see if I can scoot it a little bit. All good. But we can see on the graph, we could see in our table function, what is the x-intercept? Well, it looks like it is at the origin again, and it's not always. And we can come up with that as well by taking the numerator of the function and setting it equal to 0. I do want to look real quick here just at the domain algebraically for a minute. And the domain algebraically, what we would do is we would take x squared plus 4 and we would set it not equal to 0. When we solve that, we subtract 4 from both sides. We'll get x squared doesn't equal negative 4. And then we take the square root of both sides. And when we take the square root, we get x doesn't equal plus or minus 2i. Well, when we're dealing with domain, we're dealing with real numbers. So when we get an imaginary, or when we get an error in our table, that's when we have something that needs to be excluded from the domain. And this is not a real number, which is one of the other reasons why that is all real numbers. We looked at domain yesterday. You can look back at that video as well. So one more here on the front page, and it says, does something seem strange here? So normally what I like to do is I like to draw the graph first on the calculator. But when you see this function and you see x squared minus 4, what do you think? Maybe not so good of a question. What about the trinomial, the x squared plus 3x minus 10? What do we think when we see a trinomial like that? Factor it. And actually, it's going to be, can we factor the numerator, can we factor the denominator? So if we look at x squared minus 4, and we factor it, we get x minus 2 and x plus 2. Difference between two squares. Our denominator here can also be factored, and it's going to be x and x, and it's plus 5 minus 2. And like I say on this one, it says, does something seem strange here? Well, the one thing that we can get from the factoring right now is for our domain, we would take x plus 5 and set it not equal to 0. And consequently, we would end up with x doesn't equal negative 5. But I didn't do very well with my space. We can also take x minus 2 doesn't equal 0. And we can add 2 to both sides. And we get x doesn't equal 2. So there's two values here for our domain. But let's go and look at our picture now. And I'll type in the original function. So alpha y equals, and then we've got x squared minus 4 divided by x squared. And you could have typed in the factored version as well, plus 3x minus 10. Still give you the same answer. It's the same thing. So when we look at the picture here, there's our picture. Does anything seem strange? Well, the one thing that might seem strange is that we only have one gap in this example. And we had two values that are excluded from the domain. But if we go back and look at what we have here, even though it's scrunched in there, where is our asymptote? Is that negative 5 or is it at positive 2? And based on our picture here, it looks like our asymptote is definitely at 5. And remember, we write that as x equals 5. So when we draw that in over here, how about x equals negative 5? Get that in there eventually. And we draw it in. 1, 2, 3, 4, 5. And then we can draw our picture as well. We've got something like this. And then something. Now I'm going to look at this here, see if I can see my x-intercept. Something like that for a picture. On this one, maybe we can see the x-intercept and maybe we can't. But let's go look at our table here, because our calculator has a lot of useful parts to it, and in fact, luckily, it jumps almost right to it. If you notice, our x-intercept always has a y value of 0. So what we ended up with here is our x-intercept of negative 2, 0. That we simply got from the table. But what seems strange here is that we had two values that are excluded from the domain and only one gap in our graph, if it even seems strange. And part of the reason is, as we get ready to flip to the next page is, if we really look at this function, what we said in our first unit is, do we have anything exactly the same in the top and in the bottom? We've got x minus 2, and we've got x minus 2. And what happens is, we have to do something with that. And as I flip over here then to the next page, when we have something that's exactly the same on the top and the bottom, we have something called removable discontinuity. And what it is it's a hole in the graph. And the thing is, we can make the graph whole, W-H-O-L-E, whole again, or repairing it. We can repair it by filling in a single point. In other words, a removable discontinuity is a point at which a graph is not connected, but could be made connected again by filling in a single point. So I might have gotten a little wordy on that. Not the first time, probably won't be the last. But right beside your picture, or right beside the box there, you've got this picture. And what happens here is, if we look at this graph, we've got a hole right here. And if we go back to problem number 5, which this one coincides with, if we factor the numerator, what happens is we get x and 2 and 2, difference between two squares. And then we also have an x minus 2 in the denominator. Well, what happens is that we have something exactly the same on the top and on the bottom. We have the x minus 2. So what we have graphed over here in this line is we graphed y equals x plus 2. So here's the y-intercept, and then we went up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. But because the 2's canceled out here, or the x minus 2's canceled out, we're going to have a hole that relates back to that part of the graph. What we do is we take the value that we canceled out, the x minus 2, and we set it equal to 0. Well, you probably don't even have to do the math behind it, but just in case, we get x equals 2. That's the x value of this ordered pair here. It's going to be 2. What we do with that value of 2 is we take it and we put it back into the function part that did not cancel out. So we did not cancel out x plus 2. So we're going to take this value of 2 and we're going to put it back in here where we see the x, wherever we see x. So this is going to be the 2 plus 2, which is going to give us our y value of 4. And that's the first one that we've seen. So hopefully it made sense, but we've got a few more examples to kind of give it a chance for us to understand a little bit better. So the first one, the nice part is that it's already factored for us. We didn't have to do any of the factoring. We're going to determine the domain, the vertical asymptote, the coordinate of the discontinuity, and the x-intercept. So first of all, let's start with the domain. And again, the domain is determined by the denominator. And what we've got here is we've got that x plus 2 can't equal 0. And x plus 5 can't equal 0. Our denominator is not allowed to be equal to 0. Again, I'll show my work, but I hope that you can go directly to the fact that x doesn't equal -2. And x doesn't equal -5. That's our domain. X doesn't equal -2. X doesn't equal -5. So then, from there, what we have to determine is the vertical asymptote. Chloe? It's in the top. You only want to do the bottom. The top is going to be for our x-intercepts here. in a couple minutes. So now, vertical asymptote. The other thing that we need to notice here is that we, in this problem, happen to have an x plus 2 in the numerator and an x plus 2 in the denominator. Don't cancel out anything until you find the domain, because regardless of the problem, what's in the denominator is not part of the domain, even if you cancel it out. So what that means is, if we cancel out the x plus 2, what we're going to have for our vertical asymptote, we're not going to have this. We're simply going to have x equals -5. And we can type it in our calculator. We can look at the picture. That will be where the gap is. And what are we going to do with our other value? Well, our other value here, this -2, is going to be part of our removable discontinuity. And what we have remaining in this problem, after we canceled out the x plus 2's, is we have the function of x minus 7 divided by x plus 5. And we're going to take this value of -2, and we're going to put -2 back in for this x. In the numerator, we're going to take -2 and put it in for the x in the denominator. So it's going to be -2 minus 7. And then it's going to be -2 plus 5. Well, -2 minus 7 is -9. -2 plus 5 is 3. And -9 divided by 3 is -3. So finally, what we have to do is we have to figure out the x-intercept. But all that we need to look at in terms of the x-intercept now is the value that's remaining in our numerator, the x minus 7. So to get our x-intercept, we can take x minus 7 equals 0. And then we can add 7 to both sides, again, if you need to. If you prefer, type it in your calculator. Use your table function to get the x-intercept. Gotta press the right button. OMG. So let's try another one here. Determine the domain, the vertical asymptote, the coordinate of the removable discontinuity, and the x-intercept. So let's go back and factor here so that we can identify pieces of this function that we need to help us solve. So if we take x squared plus 10x plus 24, then we factor. We've got x and x, factors of 24 that combine to be 10. I think it's plus 4 and plus 6. And then in our denominator here, because we want to find our domain, when we factor the factors of 30 that combine to be 1, we get 6 and 5. And it's plus 6 minus 5. Once we get the function factored, we can identify our domain. And some of you might be able to look at that, and you might be able to go over here and say, well, x doesn't equal -6, and x doesn't equal 5. And I'm fine with that. I don't want to not show where that came from. We take x plus 6 and set it not equal to 0. We take x minus 5 and we set it not equal to 0. So we subtract 6 from both sides, and that's where the x doesn't equal -6. And we add 5 to both sides, and we get x doesn't equal 5. There it is. No matter what, figure out the domain before we look. Do we have anything exactly the same in the top and in the bottom? Well, we see our x equals 6. So, the fact that we canceled that out means that our only vertical asymptote is going to be x equals 5. The removable discontinuity is going to come from the value that we canceled out. So here's the 5, there's our vertical, the negative 6 down here for our removable. And when we canceled out those x plus 6's, what we still have remaining is the x plus 4 and the x minus 5. And we're going to take that value of negative 6 and we're going to put it back into our function wherever we see x. So this is going to be negative 6 plus 4. And it's going to be negative 6 minus 5. And negative 6 plus 4 is negative 2. And negative 6 minus 5 is negative 11. And negative 2 divided by negative 11 is positive 2/11. And finally, what we want to do is we want to figure out, well, what is the x-intercept? Well, we're going to find the x-intercept from the remaining part of the function. We're finding it after we cancel it out. So what we see remaining from our function is that the x plus 4 equals 0. We subtract 4 from both sides, and we get x equals negative 4. So this is going to be negative 4, 0. Again, if it's helpful, type that function into your calculator. But make sure that you factor so you can identify the domain, because you've got 2 values excluded from the domain, and you only have 1 gap in your picture. So as we finish here with our last example, can we do this when there's not really any numbers in this problem, so to speak? There are a couple of numbers, but we're not going to get an answer like x equals 5 for a vertical asymptote. So for what values of x will f of x have a vertical asymptote? Well, the process is still the same. We take our denominator values of x plus a and set it not equal to 0. And we also take 3x plus c and we set it not equal to 0. And we're just looking at the x values, which is what we do for domain anyway. But subtract a, so we get x doesn't equal negative a. And we also get, here when we subtract c, we get 3x doesn't equal negative c. And then we divide both sides by 3. So I think I can split that up. I can't. But if I scoot it down a little bit, that'll be helpful. So what we ended up with here, for what values of x will f of x have a vertical asymptote? Well, this is the domain. The only value where we're going to have a vertical asymptote is going to be in the part that doesn't cancel out. And the x plus a cancels out. So we're going to have a vertical asymptote at x equals negative c over 3. Part B. What value of x will f of x have a root or a 0? Well, what are we looking for if we're finding a root or a 0? Because we haven't used that vocabulary. what we're looking for is we're looking for an x-intercept. So how do we find the x-intercept? We're going to take the remaining value in our numerator, which is 2x minus b, and then we're going to solve for that to get our root, or 0, which is also known as an x-intercept. So if we add b to both sides, we get 2x equals b, and divide both sides by 2. So we get b over 2. So we'll add b over 2. Try to write that a little bit neater. B divided by 2. And then finally, for what value of x will we have a removable discontinuity? Well, our removable discontinuity is coming from the value that we canceled out. And that's going to be here. The x plus a canceled out. So we're going to have a removable discontinuity at the value of negative a.